Hello everyone. In this video we are going to talk about the Kruskal Wallis Test and the Bonferroni Correction. Hopefully I pronounced the names correctly. So the Kruskal Wallis H test is another non-parametric test when you are comparing three or more groups together on their average, or in this case the median. It is a non-parametric test, similar to my previous video where I talked about the Mann-Whitney test, U-test. That was a replacement for the t-test when the underlying distribution is not necessarily normal and the sample size is small, means less than 30. This is a replacement for the ANOVA, one-way ANOVA test. So if you have only one factor and you want to compare between more than two groups, like three or more, so you do the analysis of variance, this is the replacement for that when we don't know the data are normal or not. It does not require normality. And similar to ANOVA, it tells you whether there is a difference between the groups or not. It doesn't tell you which groups are different from which. You have to do some post hoc tests to do that, and I'm going to show you that one as well. So the first thing is, what are the assumptions of this test? The first one is the samples should be independent from each other and the sampling should be done randomly. The other one, the data should be I should be able to rank the data. So they should be continuous scale or ordinal. It cannot be categorical data. Now, how would you calculate the statistical value, which in this case we call it H, so H is statistics. How do you get the critical value? How do you compare? And then we go over examples and which commands in MATLAB to do that. So the first thing is, what is the hypothesis? The hypothesis, as with ANOVA in the null hypothesis, is that all these K groups, if you have K groups, they all come from the same distribution. Alternative one or H1 is they are not. Now, to calculate the H statistics, you have to have this data. First, the number of groups, then the number of data in each group. So they are not necessarily all having the same size, but most of the time they are, but sometimes they are not. Then the total number of data, which is sum of all of the sample sizes, and then sum of the ranks for each group. So what you need to do is to merge all of the data from all of the samples together and then start sorting them from the smallest to the largest and give the smallest rank 1, the largest one rank n, and if there are ties from data of different groups, you average those ranks and give the average to all of them. Now, the H statistics is equal to 12 over n times n plus 1, where n is the total number of data. Here, there is a summation that should be done in each group. So for group 1, what you do is you square the sum of the ranks for that group 1, you square it, divided by the number of data in group 1. Then you do a similar thing for group 2, group 3, all the way to group K, and add all of those R squares over n's together. And finally, minus 3 times n plus 1. So this is your H statistics. Now, how would you get the critical value? In this case, the critical value, or H critical, actually comes from a table that is not called the H table. This time, this comes from a distribution which is called the chi-squared. So the chi-squared distribution is a specific distribution that is used a lot in engineering and in statistics. And in one of my future videos, I'm going to talk about chi-square and what are the applications of this chi-square. So far, the major distributions that we talked about are mostly normal distribution and basically the student's t distribution that I use in a few of my previous videos. But there is also the chi-square distribution. And if you want to know more about different types of distributions, I have a video under this playlist, Engineering Mathematics. Let me show you that. That's this video. It's called Overview of Common PDFs and PMFs, Probability Distribution Functions and Probability Mass Functions. These are for continuous variables. These are for discrete variables. And if you go down the list, you can see at the bottom of this list, guess what? You have chi-square distribution, okay, which has the parameter k, which is the degrees of freedom. And you can see the applications is for various variance estimation and hypothesis testing and so on. So one of the things that we do in hypothesis testing is in Kruskal Wallis. Clearly, we use the data here to find the H critical. Okay, so if you want to know more about it, refer to this video. I talked a little bit about the chi-square and the applications of it and formulas of it. So here, the way to get my H critical, which is this number, I need to go to this chi-square table, and I need to get my significance level and the degrees of freedom, which in this case is number of groups minus 1. So let's say if I have 3 groups or 4 groups, let's say 3 groups, I go to 2. And then if my alpha is 0.05, I go here, and then I see that my number is 5.991, right? So here I get my H critical, and then I have H stat. And if my H stat is bigger than H critical, like the T test, like the Z test, like the F test, then I reject the H naught, reject the null hypothesis, and I conclude that there is a significance difference among the groups. If it's less than that, then I don't. Okay, I fail to reject it. So this is the chi-square distribution. And again, the chi-squared, the formula for the probability density function of that is this. It has one parameter k, the degree of freedom here. And this is the shape of it for different k values. So except for k of 1, the rest of them, and k of 2, the rest of them, they all have some kind of maximum. And then as k gets bigger and bigger, the data is further shifted to the right side. Okay, so again, I can make a separate video and talk about the applications of chi-squared distribution, but clearly you see one application is to get this H critical here. Okay, now in MATLAB, if you want to get the values or to perform this Kruskal-Wallis test, basically all you need to pass to it is the data, which is a matrix that involves the numbers from all of different groups. Then a variable group, which tells it which part of the data belongs to which group. And then you can turn on or off the results of the Kruskal-Wallis test, which is basically an ANOVA test, but non-parametric. And it can give you p-value, it can give you the table and the stats. All we really need to care about is p-value. If that p-value is bigger than my significance level, I reject the null hypothesis. Otherwise, I fail to reject it. Okay, so that command, and I'm going to show you that for this example, that is the command to perform the Kruskal-Wallis test. Now, let's look at this example. So here, let's say again, I go with that fertilizer example I use for the U test. So here again, I'm going to look at the heights of different plants or their growth of them after 4 weeks. And I want to see if these 3 different fertilizers, A, B, C, they make any difference in the growth of these plants. For each group, I measure 5 separate plants. I get 5 numbers. So I have a total of 15 data. Now, since I don't have all sorts of data here for these different fertilizers, it is not possible to see whether the underlying distribution is normal or not. So I go with the non-parametric test of Kruskal-Wallis to be safe. Now, here I'm going to use alpha of 0.05. Now, how do I do it? The first thing is I get all of these 15 numbers and I sort them from the smallest, which is 10, to the largest, which is 24. And I start giving the smallest one rank 1 all the way to the largest one, which is rank 15. And in this case, if you look, I don't have any tie. All the numbers are unique, so my ranks are uniquely from 1 to 15. And then in front of each data, I say which group it belongs to, so I can add those ranks together, right? So when I want to add ranks of group B, then I look at the data in group B and the corresponding ranks for them. So you see that the ranks are 10 and 13, and then 1, 2, and 3 on the top, correct? So I just add these 5 numbers together. I get 29. I do a similar thing for A, 37, for group C, 54. So these are some of the ranks for in the individual groups. And for all of the three groups, the number of data per group is 5. Total number of observation is 15. From there, I can go ahead and calculate my H statistics, which if I simplify, it is going to be 3.26. Now, is that significant or not? I need to go to the chi-square table. With what degree of freedom? K minus 1. Remember, I have three groups, so 3 minus 1 is 2. Alpha is 0.05. I go to that table and I find my number is 5.99, which is bigger than this. Since my stat H is less than critical, I fail to reject it. So I should say I did not find any significant difference in the plant growth using these three different fertilizers. Their effect from each other were not really significant. They were basically doing the same thing. Okay? Yes? So you see that this is basically performing the Kruskal-Wallis test or H test, non-parametric, on the data where we have no idea if the underlying distribution is normal or not. Now, first let me show you how to do it in MATLAB. So these are those data for groups ABC. I merged them basically like this in a matrix X, which in this case is a line vector really. And then you see that my group is going to be 5 A's, 5 B's, and 5 C's because that's how I sorted my data. Then I pass this group and X to Kruskal-Wallis. It gives me the stats table and P, and all I care about is P. So if I go ahead and run this, you see the P value I have is way bigger than 0.05. So because P is bigger than alpha, I cannot reject H naught. If P was less than alpha, which means a chance of way less than 5% of type 1 error, then I could reject it. Clearly, in this case, my P is big. So that means in 19%, 20% of the cases, I can see this kind of numbers, and this does not indicate that these guys are really from different kind of distribution. This is common in this distribution by 20% to make a type 1 error. And so clearly in this case you cannot reject it, as I said, and that means there is no significant difference among them. Good. Now if I and this is, by the way, it shows you also these guys. Now here you see that I did not use the option off. Since I didn't use this option off, it is going to show me the bar plots for the three groups, and it is going to show me the ANOVA table. You see, this Kruskal-Wallis is actually an ANOVA table, except no assumption on normality. And you see clearly here that this is the number that you should get from chi-squared, 326, and this is your p-value, 0.1959. And these are the three groups. As you can see, they have relatively good amount of overlap between them. They are not three separate clusters. If you look at their max, mean, average, and everything, median, ranks, and so on, you clearly see that there is a good overlap among them. So not only these three have an overlap, each pair of them, if you also look, they have a good amount of overlap. So not only in this case, the three groups, I can conclude that they are not significantly different. If I go individually and do a paired, a U-test in this case, if I do a U-test between each pair of them, the result will be the same. Not significant difference. Okay? So that's exactly our next topic. Now, based on the result of this H test, whether there is a significant difference or not, how do we determine which pairs? If there is a significant difference, how do we determine which ones are different? Right? Because let's say in this case, if I have three groups and I found in this case, if I change these numbers and I found that yes, there is a difference, how do I know which one is different from which? All three of them are different, or just A and B are different, or A and C are different? So in order to do that, as I said, for each pair of them, you have to calculate a Mann-Whitney U-test. If for each pair of groups I and J, I perform a UIJ, I get the UIJ stat from the Mann-Whitney U-test based on this formula. And if I compare it against the U critical, then I can conclude whether that pair IJ were significantly different or not. So what do I do here? I need to compare this number, which is U for group I, and this number, which is U for group J, and get the minimum of them, which is U stat, and then compare it against the U critical. If you look at my previous video where I talked about that, look. So I need U stat and I need U critical, and then U critical, if you remember, it needs 3 parameters, N1, or Ni in this case, Nj, and alpha, right? So once I compare this against the U critical, which depends on Ni and Nj and alpha, now whether it's bigger than or less than or equal or something, I can make a conclusion whether groups I and J were different or not. And if you remember, I said for the U test, the hypothesis testing is kind of backwards. If stat is less than critical, you reject it. If it's bigger than, you don't reject it. So it's kind of opposite. You see, even in H, in the H test, if you look at that, in the H test, when I reject H, my H stat should be bigger than H critical. In this case, since it wasn't, since my H stat was less than H critical, I failed to reject. But as I said, in U test is kind of the opposite. Okay? So I can do a Mann-Whitney U test on each pair, and I'm going to compare them one by one, right? Now, of course, if you have K groups, and you want to go into each pair of them, IJ, you need C of K and 2 pairs to do, which is going to be K factorial divided by K minus 2 factorial times 2 factorial. You need to make these many comparisons if you want to compare each and every one of possible pairs. Okay, if you do that, then you can compare each and every one of the pairs together. Good. So this is the post hoc test that you do to compare. Now, one thing in this post hoc test that we need to do is, because we are doing lots and lots of these pair comparisons, the chance of a type 1 error goes up. Okay, because if I do a comparison between group 1 and 2 and then group 1 and 3, when I do now group 2 and 3, this one is kind of related to the other two. Okay, this is not independent from the 2 previous tests. So if 1 and 2 were different and 1 and 3 were different, 2 and 3 could be a little bit affected by that result, or a little bit dependent on that. For that reason, I'm increasing, when I do lots of these interconnected or dependent pairs of comparisons, the chance of a type 1 error or alpha goes up automatically. So I need to artificially bring alpha down so I can keep the chance of type 1 error at a desired level. One method of changing this alpha is called the Bonferroni correction, where they divide the original alpha by C. What is C? C is the number of comparisons, number of pair comparisons that you intend to do. If you want to do all of them, this is going to be your C. You divide it by that. In this case, if I have 3 groups, I need 3 pairs. So I need to divide my alpha, which was 0.05, by 3, and use this alpha, which is like 0.0167. I need to use this alpha when I do these U tests. This way, I can control the chance of type 1 error. Good. So this is called the Bonferroni correction, which you do for post hoc test. Okay. So how do you do it? Of course, it's going to take time if you want to calculate these UIJs and do this U critical each time and do a bunch of these comparisons. In MATLAB, the command called multCompare, which I showed you in one of the previous videos, does that very fast and very accurately. All I need to pass to it is this stats that I got from my Kruskal Wallis, right? This stats that I got from this test, all I need is to pass it to it. And I say, for the correction of critical value type, use the Bonferroni. And then it gives me a result, and this result is a matrix with so many columns. The only columns I really need are the first two, which are going to tell me which pairs of groups being compared, and the last one, which is the p-value. And depending on whether that p-value is less than alpha or not, I decide whether that pair I and j were significant or not significant. Okay, so p-value for them should be less than our alpha. Good. And you might say, is this the original alpha or the modified alpha? Now, this is your original alpha that you compare against. This guy here will, when it does that p-value, it is using this adjusted alpha in itself. So when you make the final conclusion, you compare these p-values, the last column of this result, against your original alpha. You don't need to compare against the modified alpha. Now, in this case, in the case of this problem here, of course, because they were not significantly different to begin with, if I go ahead and do a multiple comparison, of course, none of the groups should be different from each other because they were not even significant to begin with. Look. So you see, pair 1 and 2, their p-value is 1, way bigger than 0.05. Pair 1 and 3, 0.68, pair 2 and 3, 0.23. You see, so none of these numbers in the third column is below 0.05, so of course, none of the groups are different. Now, if I go ahead and change my numbers and rerun the test, you can see that with these numbers, when I run, first of all, my p is clearly way less than 0.05, so there is a significant difference. But which one is different from which? I can go ahead and look at the result again, and you can see that now groups 1 and 2 are different, as well as groups 2 and 3. So 2 is clearly different from 1 and 3, and you can see why. These guys are only single-digit numbers. These guys are 3-digit numbers. These guys are 2 and 3-digit numbers. So clearly group 2 is different from 1 and 3 in this case, okay? So this is the post hoc test that you can do after the Kruskal Wallis, and for correction of alpha, you can use the Bonferroni. Hopefully this video was useful to you. I'm gonna see you in the next video.